Welcome to the Explainer. Today, we are pulling back the curtain and looking at the language computers actually speak. You know, the one that makes everything on your screen possible.
So, when a computer sees a number, let's say 26, what does it really see? Well, it's not a 2 and a 6. It's a bunch of ones and zeros. And by the time we're done here, you're going to know exactly what that string looks like, and more importantly, why.
So here's the plan. We'll kick things off with the way we count, then jump into the computer's world. After that, we'll look at a coder's secret weapon, see the brilliant shortcut that connects it all, and wrap up with why this stuff really matters. All right, let's get into it.
First up, to understand how a computer thinks, we've got to look at how we think. Okay, so to get how a computer counts, we actually have to start with us. How do we count? We use a system called Denary. You might also know it as base 10. It just means we've got 10 symbols to work with, 0 all the way up to 9, to build any number imaginable.
Now, here's the secret sauce, this idea of place value. It just means that where a digit sits changes how much it's worth. A 3 in the thousands column is obviously worth way more than a 3 in the ones column, right? That's because each spot is 10 times bigger than the one next to it. Remember that idea. It's the key to everything.
All right, let's switch gears and see how this all works when you've only got 2 fingers to count with, like a computer.
Computers run on binary, or base 2. It sounds complicated, but it's not. Everything a computer does, and I mean everything, just boils down to a huge long sequence of these 2 digits, a 1 or a 0. It's basically on or off. That's it. This is the bedrock of the entire digital world.
And check this out. It's that same place value idea again. But instead of multiplying by 10 each time, we multiply by 2. So you have the ones column, then the 2s, the 4s, the 8s, the 16s, and so on. Same concept, different base.
So, here's the problem. Computers are perfectly happy with binary. But for us humans, trying to read a long string of ones and zeros is a total nightmare. I mean, can you imagine trying to find a typo in a 24-digit binary number? No thanks.
This is a pretty big communication gap, right? We need some kind of bridge, a way to squish that long binary information into something our brains can actually handle.
And that's where hexadecimal comes in. You can think of it as the perfect shorthand for binary. It's a base 16 system that was basically invented to make raw binary data easy for people to read.
So how do you get 16 digits? Well, you start with what you know, 0 through 9. And then you just keep going. We use the letters A through F to stand in for the values 10 through 15. Simple as that.
So, why does this work so well? How do these two systems connect so perfectly? This isn't just a happy accident. This is where the real genius is. It's all by design.
And here is the secret sauce. The whole reason hex is so useful is that one single hex digit perfectly lines up with a group of 4 binary digits. 4 bits. And get this, that group of 4 bits has a technical name. It's called a nibble. Seriously. A byte is 8 bits, so a nibble is, half a byte.
Because of that neat trick, converting from binary to hex is super simple. It's just a 3-step process. You chop your binary into those 4-bit nibbles, you convert each little chunk on its own, and then you just stick the results together. It's less like math and more like using a secret decoder ring.
And this table right here, this is our Rosetta Stone. This is the decoder ring. It shows you how every single possible 4-bit combination, from 4 zeros to 4 ones, maps directly to one hex character, from 0 to F. This is the key to the whole shortcut.
Okay, let's do a quick example so you can see just how easy this is. We're going to take this 8-bit number and shrink it down. So first step, we take our binary number and we split it right down the middle. We're breaking it into 2 4-bit nibbles. Now that we've got our 2 little chunks, we can just handle them one at a time. Much easier to work with. Now we just go back to our Rosetta Stone. We look up the first nibble, 1011. The table tells us that's the number 11 in our system, which is B in hex. Then we look up the second nibble, 0111, and that's just a plain old 7.
Slap them together, and you're done. That long, clunky binary string 10110111 becomes the nice, clean, simple value B7. Way easier to write down and remember, right?
Okay, so why do we care about all this? Because it's not just about counting. This is how computers represent, well, everything. All information. Every piece of text, every image, every sound. It's all just numbers under the hood.
Think about the words you're reading on the screen.
Each letter is really just a number. There's a standard called ASCII that says, for example, a capital A is the number 65. The computer stores 65 in binary, and a programmer debugging the code might look at it in hex to make their life easier.
So that leaves us with a pretty mind-bending thought, doesn't it? In this digital universe we've built, where literally everything is just a number, what happens to the things that can't be turned into a number? For a computer, do they even exist at all? It's a question that really gets to the core of what digital information truly is and what it isn't.